Introduction to TCP. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this comprehensive series, we will explore the Transmission Control Protocol, commonly known as TCP. TCP is one of the most fundamental protocols in computer networking, forming the backbone of reliable internet communication. Understanding TCP deeply is essential for network engineers, system administrators, security professionals, and anyone working with networked applications. TCP operates at the transport layer, which is layer 4 of the OSI model. The transport layer sits between the network layer below it and the session layer above it. Its primary responsibility is to provide end-to-end communication services for applications. While the network layer handles routing packets between different networks, the transport layer ensures that data arrives completely and in the correct order at the destination application. Let me walk you through the diagram showing the OSI model layers. The diagram illustrates the 7 layers of the OSI model stacked vertically. The application layer handles high-level protocols and user interface functions. The presentation layer manages data formatting and encryption. The session layer establishes and manages connections between applications. The transport layer, highlighted as our focus area, provides reliable data transfer services. The network layer handles logical addressing and routing. The data link layer manages physical addressing and frame transmission. Finally, the physical layer deals with the actual transmission of raw bits over physical media. TCP provides several critical services that make it indispensable for applications requiring reliable data transfer. These include connection-oriented communication, which means a connection must be established before data transfer begins. TCP also provides reliable delivery through acknowledgment mechanisms, ensuring no data is lost in transit. Additionally, TCP handles flow control to prevent overwhelming the receiver, congestion control to prevent network overload, and in-order delivery to ensure data arrives in the sequence it was sent. TCP Header Structure Overview. Understanding the TCP header structure is fundamental to comprehending how TCP achieves its reliability and connection management. The TCP header contains all the control information needed for reliable, ordered data delivery. Let us examine each field in detail. The TCP header begins with the source port field, occupying 16 bits. This field identifies the sending application's port number, which ranges from 0 to 65535. Port numbers below 1024 are considered well-known ports reserved for standard services, while ports from 1024 to 49151 are registered ports, and ports from 49152 to 65535 are dynamic or private ports used for ephemeral connections. Following the source port is the destination port field, also 16 bits. This identifies the receiving application's port number. Together, the source and destination ports, combined with source and destination IP addresses from the IP header, uniquely identify a TCP connection. This 4-tuple ensures that multiple connections can exist simultaneously between the same two hosts. The sequence number field occupies 32 bits and serves as the cornerstone of TCP's reliable delivery mechanism. This number identifies the position of the first byte of data in this segment within the overall data stream. If the sequence number is 1000 and the segment contains 100 bytes, the next expected sequence number would be 1100. During connection establishment, each side chooses an initial sequence number randomly for security purposes. The acknowledgment number field, also 32 bits, works in conjunction with the sequence number. When the ACK flag is set, this field contains the next sequence number the receiver expects. This value essentially acknowledges all bytes up to but not including this number. For example, an acknowledgement number of 1100 confirms receipt of all bytes through sequence number 1099. The data offset field, sometimes called header length, is 4 bits and specifies where the data begins. Since the TCP header can include optional fields, this value indicates the header length in 32-bit words. The minimum value is 5, representing 20 bytes, and the maximum is 15, representing 60 bytes when options are present. The reserved field is 3 bits set aside for future use. These bits must be set to 0 in current implementations. Following this are the TCP flags, which we will examine in detail on the next slide. TCP control flags. The TCP control flags, sometimes called control bits, occupy 9 bits in the TCP header and govern the behavior of the TCP connection. Each flag serves a specific purpose in connection management and data transfer. Understanding these flags is essential for analyzing TCP behavior and troubleshooting network issues. The SYN flag, which stands for synchronize, initiates a connection and synchronizes sequence numbers between the communicating parties. When a client wants to establish a connection, it sends a segment with the SYN flag set. The server responds with both SYN and ACK flags set. The SYN flag is only used during the initial connection establishment. The ACK flag indicates that the acknowledgement number field is valid and should be processed. After the initial SYN segment, virtually all segments in a TCP connection have the ACK flag set. This flag confirms receipt of data and is the foundation of TCP's reliable delivery mechanism. The FIN flag, meaning finish, signals that the sender has finished sending data and wants to close the connection. Unlike an abrupt termination, FIN allows for graceful connection closure, ensuring all data has been received before the connection terminates. Both sides must send a FIN to completely close the connection. The RST flag, meaning reset, abruptly terminates a connection or rejects an invalid segment. When a host receives a segment for a connection that does not exist, it responds with RST. This flag is also used when an application wants to immediately abort a connection without the graceful FIN exchange. The PSH flag, meaning push, tells the receiving TCP stack to immediately deliver this data to the application rather than waiting for more data to fill the buffer. This is useful for interactive applications where latency is critical, such as terminal sessions. The URG flag indicates that the urgent pointer field is valid and contains urgent data that should be prioritized. The ECE and CWR flags support explicit congestion notification, allowing routers to signal congestion before packet loss occurs. The NS flag is the ECN nonce concealment protection flag, used to protect against accidental or malicious concealment of marked packets. The diagram shows all 9 TCP flags arranged in their header position. From the diagram, we see URG for urgent data indication, ACK for acknowledgement validation, PSH for push function, RST for connection reset, SYN for sequence synchronization, and FIN for connection termination. Additionally, NS, CWR, and ECE flags support the explicit congestion notification mechanism. Three-way handshake Step 1 SYN. Let us now examine each step of the three-way handshake in detail, starting with the first step where the client initiates the connection by sending a SYN segment. When an application on the client wants to establish a TCP connection, it triggers the operating system's TCP stack to begin the handshake. The client constructs a TCP segment with specific characteristics. The SYN flag is set to 1, indicating this is a synchronization request. The sequence number field contains the client's initial sequence number, which the client generates randomly. The initial sequence number, or ISN, is a critical security and reliability feature. Historically, ISNs were predictable, which allowed attackers to forge packets and hijack connections. Modern TCP implementations use cryptographically random ISNs to prevent such attacks. The ISN represents the sequence number of the first byte that will be sent. When we say the ISN is 1000, the first actual data byte will be numbered 1000. During this first step, the client also advertises its receive window size, indicating how much buffer space it has available for incoming data. Additionally, The client may include TCP options in this segment. Common options sent during SYN include the maximum segment size option, which tells the server the largest segment the client can receive. The window scale option may be included if the client wants to support windows larger than 5535 bytes. The selective acknowledgment permitted option indicates the client supports SACK. Timestamp options may also be included for round-trip time measurement. The diagram illustrates the first step of the handshake. The client prepares its SYN segment, setting the SYN flag to 1, choosing a random initial sequence number, setting the acknowledgement number to 0 since nothing has been received yet, advertising its window size, and including negotiation options. This prepared segment then travels across the network to reach the server. The server receives this segment and now knows the client's sequence number and capabilities. After sending the SYN segment, the client enters the SYN sent state and starts a timer. If no response arrives before the timer expires, the client will retransmit the SYN segment. This retransmission uses exponential backoff, meaning each subsequent retry waits longer than the previous one. Three-way handshake. Step 3. Acknowledge. The third and final step of the three-way handshake occurs when the client receives the server's SYN-ACK segment and responds with an ACK segment. This final message completes the connection establishment, and both parties can begin exchanging data. When the client receives the SYN ACK, it validates several things. It confirms the acknowledgement number matches its ISN +1, verifying the server correctly received and processed the SYN. It records the server's ISN from the sequence number field. It processes the server's TCP options and adjusts its behavior accordingly. The client then constructs the final ACK segment. Only the ACK flag is set to 1. The SYN flag is not set because sequence number synchronization is complete. The sequence number field contains the client's ISN +1. Since the SYN flag consumed one sequence number even though no data was sent. The acknowledgement number contains the server's ISN +1, confirming receipt of the server's SYN. A unique aspect of this third segment is that it can carry data. While the first two segments of the handshake cannot contain application data, the final ACK can piggyback data if the application has something to send immediately. This optimization saves a round trip in protocols where the client sends data first, such as HTTP. The diagram illustrates this final step. The client receives the server's SYN ACK and prepares the final ACK segment. The client sets only the ACK flag to 1, sets the sequence number to its ISN +1, sets the acknowledgement number to the server's ISN +1, and may optionally include application data. This ACK segment travels to the server. Upon receiving this ACK, the server transitions to the established state. The client also enters the established state after sending this segment. Once both sides are in the established state, the connection is fully operational. Data can flow in both directions simultaneously, as TCP provides full duplex communication. Each direction of data flow operates independently with its own sequence numbers and acknowledgements. Complete handshake sequence diagram. Now let us examine the complete three-way handshake as a unified sequence, showing all messages and state transitions together. This comprehensive view helps understand the timing and relationship between each step of the process. The sequence diagram shows the complete handshake from start to finish. Initially, both client and server are in the closed state, meaning no connection exists. The client initiates the process by transitioning to the SYN sent state and transmitting a SYN segment. This segment contains the flag setting SYN = 1, the client's randomly chosen sequence number of 100 in this example, and a window size of 65535 bytes. The server receives this SYN segment while in the listen state, which means it is waiting for incoming connection requests on a specific port. Upon receiving the SYN, the server transitions to the SYN received state and sends back its SYN ACK response. This response contains SYN and ACK flags both set to 1, the server's sequence number of 300 in this example, an acknowledgement number of 101, which is the client's sequence number plus 1, and the server's window size of 32,768 bytes. The client, still in SYN sent state, receives this SYN ACK and validates it. The acknowledgement number of 101 confirms the server received the client's SYN. The client records the server's sequence number of 300. The client then transitions to the established state and sends the final ACK segment. This segment has only the ACK flag set to 1, a sequence number of 101, and an acknowledgement number of 301, which is the server's sequence number plus 1. When the server receives this final ACK, it transitions to the established state as well. At this point, both sides have completed their state transitions. Both have each other's sequence numbers. Both have agreed on window sizes and options, and the connection is ready for data transfer. The entire handshake typically completes in 1.5 round-trip times. The half comes from the fact that data can begin flowing before the third ACK arrives at the server, as the client considers the connection established as soon as it sends the ACK. This is why measuring connection establishment time from the client's perspective differs from the server's perspective. Understanding sequence numbers. Welcome back to our TCP Deep Dive series. In this section, we will explore one of the most critical aspects of TCP, the sequence number mechanism. Sequence numbers are the foundation upon which TCP builds its reliable delivery guarantees, and understanding them thoroughly is essential for troubleshooting network issues and optimizing application performance. Every byte of data transmitted over a TCP connection is assigned a unique sequence number. This is not just a counter for segments. It is a byte-level tracking system. When we say a segment has sequence number 1000 and contains 100 bytes of data, we mean that the first byte of that segment is byte number 1000, the second byte is 1001, and the last byte is 1099. The next segment would then start with sequence number 1100. The sequence number field in the TCP header is 32 bits wide, allowing for sequence numbers from 0 to 4, 294, 967, 295. This is approximately 4.3 billion unique values. On high-speed networks, this sequence space can be exhausted relatively quickly. A 10 gigabits per second link can transmit 4 gigabytes in about 3.4 seconds, meaning sequence numbers could wrap around in that time. This wraparound is handled by TCP and is one reason why timestamp options are important for very high-speed connections. Let me walk through the sequence number diagram. The diagram shows a data stream as the starting point, representing the continuous flow of application data. This stream connects to a byte numbering process where each byte receives a unique sequential number. From there, the numbered bytes flow into segment creation where bytes are grouped into transmission units. Each segment then receives a sequence number assignment based on its first byte's position. Finally, segments are placed in the transmission queue ready for sending over the network. The entire flow demonstrates how TCP transforms a continuous data stream into trackable, sequenced segments. The initial sequence number, or ISN, is chosen at connection establishment and is not zero. Modern implementations use random ISN generation for security. If ISNs were predictable, an attacker could forge packets that appear to belong to an existing connection. By randomizing the ISN, TCP makes such attacks significantly more difficult. The acknowledgment mechanism. The acknowledgment mechanism is TCP's primary tool for ensuring reliable delivery. Every byte of data sent must eventually be acknowledged by the receiver, or the sender will retransmit it. This creates a robust system where data loss is detected and corrected automatically. TCP uses cumulative acknowledgments, meaning an acknowledgement number confirms receipt of all bytes with sequence numbers less than the acknowledgement number. If a sender transmits bytes 1000 through 1999 and receives acknowledgement number 2000, it knows all those bytes arrived successfully. The sender can then free the buffer space used to store those bytes in case retransmission was needed. The acknowledgement process is not instantaneous. Receivers typically implement delayed acknowledgments, waiting briefly before sending an ACK in case more data arrives that can be acknowledged together. This delay is usually around 200 milliseconds but varies by implementation. The delay reduces the number of small ACK packets on the network, improving efficiency. However, if two full-sized segments arrive, the receiver sends an immediate acknowledgement. This ensures the sender receives timely feedback when data is flowing continuously. The delayed ACK mechanism is a trade-off between responsiveness and network efficiency. The diagram shows the acknowledgement flow in detail. The sender transmits a data segment to the receiver, which includes the sequence number and payload. Upon receiving the segment, the receiver processes the data and prepares a response. The receiver then sends an ACK segment back to the sender containing the acknowledgement number, which represents the next expected sequence number. The sender receives this acknowledgement and updates its state, marking those bytes as successfully delivered. The sender can now free the send buffer space for those acknowledged bytes and advance to sending new data. When data is flowing in both directions, acknowledgements can be piggybacked on data segments. Instead of sending a separate ACK packet, the receiver includes the acknowledgement in its next data segment. This piggybacking is automatic and reduces packet count on the network. Calculating retransmission timeout. The retransmission timeout calculation is based on algorithms defined in RFC 6298. This RFC specifies how TCP should measure round-trip times and derive appropriate timeout values. Understanding this calculation helps explain TCP behavior under various network conditions. TCP maintains two state variables for RTO calculation. The first is SRTT, which stands for smooth round-trip time. This is a weighted average of observed RTT measurements. The second is RTT-VAR, which stands for RTT variance. This measures the variability in round-trip times. When TCP receives the first RTT measurement, denoted R, it initializes SRTT to R and RTT-VAR to R divided by 2. For subsequent measurements, TCP updates these values using exponential weighted moving averages. The RTT-VAR update uses a factor of 1/4, meaning new variance measurements receive 25% weight while historical variance retains 75% weight. The SRTT update uses a factor of 1/8, giving new RTT measurements 12.5% weight. The RTO itself is calculated as SRTT plus 4 times RTT-VAR. This formula ensures the RTO is at least 1 SRTT plus a margin for variance. The factor of 4 on RTT-VAR provides a safety margin that accounts for network jitter. RFC 6298 also specifies that RTO should have a minimum value, typically 1 second, to prevent overly aggressive retransmissions. The code block shows the complete algorithm. Starting with the first RTT measurement R, SRTT is set equal to R and RTT-VAR is set to R divided by 2. For each subsequent measurement R', RTT-VAR is updated by multiplying current RTT-VAR by 0.75 and adding 0.25 times the absolute difference between SRTT and R'. Then SRTT is updated by multiplying current SRTT by 0.875 and adding 0.125 times R'. Finally, RTO is calculated as SRTT plus 4 times RTT-VAR, with a minimum bound of 1 second. This algorithm adapts quickly to increasing delays through the variance term while remaining stable during normal operation through the smoothed average. It represents decades of research into optimal TCP behavior. TCP send and receive buffers. TCP maintains buffers on both the sending and receiving sides to manage data flow. Understanding these buffers is essential for performance tuning and troubleshooting throughput issues. The send buffer, also called the write buffer, holds data that the application has passed to TCP but has not yet been acknowledged by the receiver. This buffer serves two purposes. First, it queues data waiting to be transmitted. Second, it retains transmitted data until acknowledgement arrives, enabling retransmission if needed. The send buffer size limits how much unacknowledged data can be in flight. The receive buffer holds data that has arrived from the network but has not yet been read by the application. When segments arrive, TCP places the data in the receive buffer in sequence order. The application reads from this buffer at its own pace. If the application reads slowly, the buffer fills up, eventually causing TCP to reduce the advertised window and slow the sender. The diagram illustrates the complete buffer architecture. On the sending side, the application writes data into the send buffer. The TCP stack takes data from the send buffer and transmits it over the network. On the receiving side, data arrives from the network and the TCP stack places it into the receive buffer after reordering if necessary. The application then reads data from the receive buffer when ready. Two feedback mechanisms exist. The acknowledgement feedback flows from the receiving TCP stack back through the network to the sending TCP stack, informing it which bytes have been received. The window advertisement is included in these acknowledgments, telling the sender how much receive buffer space remains available. Buffer sizes are configurable and significantly impact performance. Larger buffers allow more data in flight, which is necessary for high bandwidth delay product networks. However, excessively large buffers can cause buffer bloat, where too much data queues in the network, increasing latency. Modern systems often use buffer auto-tuning to adjust sizes dynamically based on connection characteristics. Reliable delivery guarantees. TCP provides several guarantees that together constitute its reliable delivery service. Understanding these guarantees helps explain why TCP behaves as it does and when its overhead may or may not be necessary for your application. The first guarantee is delivery assurance. If TCP accepts data from an application, it will deliver that data to the remote application or report an error. Data does not silently disappear. This guarantee is achieved through the acknowledgement and retransmission mechanisms we have discussed. The second guarantee is ordering. Data arrives at the receiving application in exactly the same order it was sent by the sending application. Even if packets take different paths through the network and arrive out of order, TCP reassembles them correctly before delivering to the application. This ordering is achieved through sequence numbers. The third guarantee is no duplication. Each byte of data is delivered exactly once. Even though TCP may retransmit segments and those segments may arrive multiple times due to spurious retransmissions, TCP uses sequence numbers to detect and discard duplicates. The application never sees duplicate data. The fourth guarantee is error detection. TCP uses checksums to verify data integrity. If a segment arrives with a corrupted payload or header, the checksum will not match, and TCP will silently discard the segment. The sender will eventually retransmit when acknowledgement does not arrive. The diagram presents these four guarantees as pillars supporting TCP reliable delivery. The delivery guarantee pillar shows how data is always delivered or errors are reported, never lost silently. The ordering guarantee pillar demonstrates that data arrives in send order through sequence number tracking. The no duplication pillar explains that each byte arrives exactly once using duplicate detection. The error detection pillar shows how checksums catch corrupted data. All four pillars connect to and support the overarching TCP reliable delivery mechanism that applications depend upon. Byte stream abstraction. TCP presents a byte stream abstraction to applications, which is fundamentally different from the packet-based reality of network communication. This abstraction simplifies application development but has important implications that developers should understand. From the application's perspective, TCP provides two continuous streams of bytes, one in each direction. The application writes bytes to its send stream, and they eventually appear in the remote application's receive stream. The application does not see or control segment boundaries. It simply writes and reads bytes. The sending TCP implementation decides how to segment the byte stream into packets. It considers factors like the maximum segment size negotiated during the handshake, the Nagel algorithm which we will discuss later, available data in the send buffer, and current network conditions. 2 writes of 100 bytes each might go in one segment or two, and the application has no direct control over this. Similarly, the receiving application cannot assume any relationship between send operations and receive operations. If the sender writes 100 bytes, then 50 bytes, then 150 bytes, the receiver might read all 300 bytes in one operation, or receive 200 then 100, or any other combination. The only guarantee is that the bytes arrive in order. The diagram illustrates this byte stream concept. The sending application performs 3 write operations, writing 100 bytes, then 50 bytes, then 150 bytes to TCP. The TCP segmentation layer receives these writes and makes its own decisions about segmentation, producing segments that may not align with application writes. These segments traverse the network independently. The TCP reassembly layer on the receiving side collects arriving segments and reassembles them into a continuous byte stream. Finally, the receiving application performs read operations that retrieve bytes from this stream. The read sizes of 120, 80, and 100 bytes shown in the diagram do not match the original write sizes, demonstrating that TCP does not preserve application message boundaries. If an application needs message boundaries preserved, it must implement its own framing protocol on top of TCP. This might involve length prefixes, delimiters, or fixed-size messages. Many application protocols like HTTP include such framing mechanisms to delineate requests and responses within the TCP byte stream. Introduction to Flow Control. Welcome back to our TCP series. In this section, we explore one of TCP's most elegant mechanisms, flow control. Flow control ensures that a fast sender does not overwhelm a slow receiver, preventing data loss and maintaining efficient communication between systems with different processing capabilities. The fundamental problem flow control solves is the mismatch between sending and receiving speeds. Consider a powerful server sending data to a mobile device with limited processing power. Without flow control, the server could transmit data faster than the mobile device can process it, causing buffer overflow and packet loss. Flow control provides a feedback mechanism that allows the receiver to control the rate at which the sender transmits. TCP implements flow control through the advertised window mechanism, also called the receive window. Each TCP segment contains a window field in the header that tells the sender how much buffer space the receiver currently has available. The sender must not have more unacknowledged data in flight than the receiver's advertised window allows. Let me explain the flow control diagram. The diagram illustrates the relationship between the sender and receiver in a flow-controlled communication. The sender maintains a send buffer containing data waiting to be transmitted. Data flows from the sender through the network to the receiver. The receiver has a receive buffer that holds incoming data until the application reads it. The application processes data from the receive buffer at its own pace. A critical feedback loop exists where the receiver sends window updates back through the network to the sender. These updates inform the sender of current buffer availability, allowing the sender to adjust its transmission rate accordingly. The entire system creates a closed loop where receiver capacity directly governs sender behavior. Flow control operates end-to-end between the TCP endpoints. It is distinct from congestion control, which we will cover later. Flow control protects the receiver from being overwhelmed, while congestion control protects the network from being overwhelmed. Both mechanisms use windows to limit the amount of data in flight, but they respond to different signals. The sliding window protocol. The sliding window protocol is the algorithmic foundation of TCP's data transfer mechanism. It allows efficient use of network bandwidth by permitting multiple segments to be in transit simultaneously, while maintaining flow control and enabling reliable delivery. The name sliding window comes from the visualization of the protocol's operation. Imagine the entire data stream as a long sequence of bytes. A window of allowed transmission slides along this sequence as data is sent and acknowledged. The left edge of the window represents the oldest unacknowledged byte. The right edge represents the limit of what the sender may transmit based on the receiver's advertised window. The sender's view of the data stream is divided into 4 categories. First, bytes that have been sent and acknowledged, which are to the left of the window and can be discarded from the send buffer. Second, bytes that have been sent but not yet acknowledged, which are within the window and must be retained for possible retransmission. Third, bytes that are ready to send and allowed by the window, which are within the window but not yet transmitted. Fourth, bytes that cannot be sent until the window advances, which are to the right of the window. The diagram visualizes the sliding window from the sender's perspective. The entire data stream is shown as a continuous sequence. The sent and acknowledged section contains bytes 1 through 1000, which have been successfully delivered and acknowledged, so the sender no longer needs to track them. The sent not acknowledged section contains bytes 1001 through 3000, which are in transit or awaiting acknowledgement and must be kept in the buffer for potential retransmission. The consent section contains bytes 3001 through 5000, which fall within the current window and may be transmitted immediately. The cannot send section contains bytes 5001 onward, which exceed the current window and must wait until the window advances through acknowledgements. The window spans from byte 1001 to 5000, a total of 4000 bytes as advertised by the receiver. As acknowledgements arrive, the left edge of the window slides right, allowing new bytes at the right edge to become sendable. This continuous sliding motion is why the protocol earned its name. The window never shrinks from the right, only grows as acknowledged data slides out from the left. Window updates in zero window. The received window size is not static. It changes based on how quickly the receiving application consumes data from the buffer. Understanding window dynamics, including the zero window condition, is important for diagnosing performance issues. When the receiving application reads data from the receive buffer, space becomes available, and the receiver can advertise a larger window. Conversely, if data arrives faster than the application processes it, the buffer fills up, and the advertised window shrinks. In extreme cases, the window can reach zero. A zero window condition occurs when the receiver's buffer is completely full. The receiver advertises a window of zero, telling the sender it cannot accept any more data. The sender must stop transmitting and wait for a window update indicating space is available again. To prevent deadlock when the window is zero, TCP uses a mechanism called zero window probing or persist timer. The sender periodically sends small probe segments to solicit a window update from the receiver. Without this mechanism, the sender might wait forever if a window update packet is lost in transit. The diagram illustrates the zero window scenario and recovery. The sender transmits data to the receiver, which stores it in its buffer. Eventually, the receiver's buffer becomes full because the application is processing data slowly. The receiver sends a segment with window equals 0, signaling the buffer is full. The sender receives this and enters a waiting state. The sender starts a persist timer to avoid deadlock. When the timer expires, the sender transmits a window probe, a small segment designed to elicit a response. Meanwhile, the application continues processing data, freeing buffer space. The receiver responds to the probe with a window update showing available space. The sender receives this update and resumes normal data transmission. This mechanism ensures communication can resume even if a window update is lost. Zero window conditions are normal in some scenarios, such as when a receiver is handling intensive processing. However, frequent or prolonged zero windows may indicate a performance bottleneck in the receiving application. Receive window versus congestion window. TCP actually uses two windows to control data transmission: the receive window and the congestion window. Understanding the distinction between these windows is crucial for comprehending TCP performance under various network conditions. The receive window, which we have been discussing, is determined by the receiver and communicated through the window field in TCP segments. It represents the receiver's buffer capacity and implements flow control. The receiver calculates this value based on how much space is available in its receive buffer. The congestion window, abbreviated CWND, is maintained by the sender and is never communicated in TCP segments. It represents the sender's estimate of how much data the network can handle without causing congestion. The sender adjusts this value based on signals like packet loss and explicit congestion notifications. The effective window, which determines how much data the sender can actually have in flight, is the minimum of the receive window and the congestion window. Even if the receiver advertises a large window, the sender will limit itself if it believes the network is congested. Conversely, even if the network has ample capacity, the sender respects the receiver's advertised window. The diagram illustrates the relationship between these windows. The receiver calculates and advertises the receive window, also known as rwnd, which flows to the sender. Independently, the sender maintains the congestion window, also known as CWND, based on network feedback. Both windows feed into a minimum calculation. The output of this calculation is the effective window, which represents the actual amount of data the sender may have unacknowledged at any time. The effective sending limit is always the more restrictive of the two windows. If rwnd is 32 KB and CWND is 16 KB, the sender is limited to 16 KB in flight. If rwnd is 16 KB and CWND is 32 KB, the sender is limited to 16 KB in flight. Both constraints must be satisfied. We will explore the congestion window in detail when we cover congestion control. For now, remember that flow control via the receive window prevents receiver overflow, while congestion control via the congestion window prevents network overload. Receiver-side flow control implementation. Implementing flow control on the receiver side involves careful buffer management and strategic window advertisement. The receiver must balance responsiveness with efficiency, avoiding both silly window syndrome and unnecessary delays. When data arrives, the receiver places it in the receive buffer in sequence order. Out-of-order data is also buffered, waiting for missing segments to arrive. The available window is calculated as total buffer size minus currently buffered data. However, the receiver does not always advertise this exact value. To avoid silly window syndrome, receivers implement delayed window updates. After advertising a zero or small window, the receiver waits until at least one maximum segment size of space is available, or until half the total buffer is free, before advertising a larger window. This ensures the sender can transmit efficiently sized segments. The receiver also implements delayed acknowledgments. Instead of immediately acknowledging every segment, the receiver waits briefly, typically 200 milliseconds, hoping to piggyback the acknowledgement on outgoing data or to acknowledge multiple segments at once. However, the receiver never delays beyond 2 full segments, ensuring timely feedback to the sender. The diagram shows the receiver-side flow control algorithm as a decision tree. When a segment arrives, the receiver first performs buffer management, placing data in the receive buffer in sequence. Next comes window calculation, determining available buffer space. Then a decision point asks whether the available space is greater than MSS or half the buffer size. If yes, the receiver proceeds to advertise window, sending the new window value in the next ACK. If no, the receiver moves to delay update, waiting until more space is available before advertising. In both paths, the final step is send ACK, which returns the acknowledgement to the sender. This algorithm prevents advertising small windows that would trigger inefficient small segment transmissions. These receiver-side behaviors interact with sender-side mechanisms like the Nagel algorithm to create an efficient system that avoids both wasted bandwidth and unnecessary delays. Flow control summary. Flow control is a fundamental TCP mechanism that prevents fast senders from overwhelming slow receivers. Through the advertised window, receivers communicate their capacity, and senders respect these limits. This creates a self-regulating system that adapts to varying receiver processing speeds. The sliding window protocol enables efficient data transfer by allowing multiple segments in flight simultaneously. As acknowledgments arrive, the window slides forward, making room for new data. This pipelining is essential for achieving high throughput, especially on high-latency links. Window dynamics introduce complexity that can affect performance. Zero-window conditions require special handling through persist timers. Silly window syndrome wastes bandwidth with small segments. The 16-bit window field limits throughput on high bandwidth, high latency paths until window scaling is employed. The receive window works alongside the congestion window to determine the effective sending rate. While flow control protects the receiver, congestion control protects the network. The sender always respects both limits, transmitting at the rate allowed by the more restrictive window. The summary diagram recaps all the key flow control concepts. TCP flow control connects to four major components. The receive window component manages buffer-based limitation and is advertised in every segment. The sliding window component enables pipelining for efficient data transfer with its window advancing on ACK. The window dynamics component handles zero window through the persist timer and avoids SWS through delayed updates. The effective window component shows the interaction between rwnd and cwnd, taking the minimum of both. All these components work together to create a robust flow control system that adapts to receiver capacity while maximizing throughput. The result is reliable, efficient data transfer that respects endpoint constraints. In the next section, we will explore TCP options in detail, including the window scale option that overcomes the 16-bit window limitation, maximum segment size negotiation, selective acknowledgement for efficient loss recovery, and timestamps for RTT measurement and protection against wrapped sequence numbers. Introduction to TCP options. Welcome back to our TCP series. Options allow TCP to negotiate enhanced features, optimize performance, and adapt to modern network conditions that were not anticipated when TCP was originally designed. In this section, we explore TCP options, which extend the protocol's capabilities beyond what the fixed header provides. The TCP header includes a fixed 20-byte portion containing the essential fields we have already discussed, such as ports, sequence numbers, acknowledgement numbers, flags, and window size. Following this fixed portion is a variable length options section that can add up to 40 additional bytes, bringing the maximum header size to 60 bytes. Options are negotiated during the three-way handshake. The client includes desired options in its SYN segment, and the server responds with its own options in the SYN ACK. Options that require mutual agreement, like window scale and SACK permitted, must be offered by both sides to be enabled. Options that are informational, like maximum segment size, only need to be sent by one side to inform the other. The diagram shows the structure of a TCP header with options. The fixed header section contains the mandatory 20 bytes including source port, destination port, sequence number, acknowledgement number, data offset, flags, window, checksum, and urgent pointer. Following this, the options section contains variable length option data. Common options shown include MSS for maximum segment size, W-scale for window scale factor, SACK permitted indicating selective acknowledgement support, and timestamps for RTT measurement. The options section connects to padding, which ensures the header ends on a 32-bit boundary. Finally, the data payload contains the actual application data being transmitted. The data offset field in the fixed header indicates where the data begins, effectively specifying the header length. This 4-bit field expresses the header length in 32-bit words. A value of 5 means 20 bytes with no options, while a value of 15 means 60 bytes with maximum options. Maximum segment size option. The maximum segment size option, commonly called MSS, is one of the most important TCP options. It specifies the largest segment a host is willing to receive. Proper MSS negotiation is crucial for avoiding fragmentation and achieving optimal throughput. MSS represents the maximum amount of data in a single TCP segment, not including the TCP header or IP header. It is distinct from the maximum transmission unit, or MTU, which is the maximum size of an entire IP packet including all headers. The relationship is that MSS equals MTU minus the IP header size minus the TCP header size. For standard IP version 4 with no options, this means MSS equals MTU minus 40 bytes. The MSS option is sent only in SYN segments during connection establishment. Each side independently advertises its MSS to inform the other of its receiving capability. A host will never send a segment larger than the MSS advertised by its peer. If no MSS option is present, the default value of 536 bytes is assumed, which corresponds to the minimum MTU of 576 bytes that all IP hosts must support. The diagram shows how MSS relates to MTU in segment structure. Starting with the total MTU, which is typically 1,500 bytes for Ethernet, the IP header consumes 20 bytes, and the TCP header consumes another 20 bytes minimum. The remaining space is the MSS, calculated as MTU minus 40, yielding 1460 bytes for standard Ethernet. The segment structure shows these components assembled. IP header followed by TCP header followed by TCP data. The TCP data portion equals the MSS value. This calculation ensures that TCP segments fit within a single IP packet without requiring fragmentation at the IP layer. Choosing the correct MSS is important. If MSS is too large, IP fragmentation occurs, which is inefficient and problematic if fragments are lost. If MSS is too small, header overhead increases and throughput decreases. Most systems automatically derive MSS from the interface MTU, ensuring optimal sizing for the LAN. Window scale option. The window scale option solves the 16-bit window field limitation we discussed earlier. Without scaling, the maximum window is 65,535 bytes, which severely limits throughput on high bandwidth, high latency networks. Window scaling multiplies the window field by a power of 2, enabling windows up to 1 GB. The window scale option is negotiated during the three-way handshake. Both sides must include the option in their SYN segments for scaling to be enabled. The option contains a single byte specifying the scale factor, which ranges from 0 to 14. The actual window size is calculated by taking the value in the window field and shifting it left by the scale factor, which is equivalent to multiplying by 2 raised to the scale factor power. For example, if the scale factor is 7, each unit in the window field represents 128 bytes instead of 1 byte. A window field value of 512 would represent an actual window of 512 times 128, which equals 65,536 bytes. With maximum scaling of 14, the effective window can reach 65,535 times 16,384, which equals approximately 1,073,725,440 bytes or about 1 GB. The diagram demonstrates window scaling calculation. The window field contains the raw 16-bit value, shown as 512 in this example. The scale factor of 7 means multiply by 2 to the power of 7, which equals 128. The multiplication operation takes the window field value of 512 and multiplies by the scale factor of 128, yielding an effective window of 65,536 bytes. The diagram also shows the general formula where effective window equals window field times 2 raised to the scale factor power. Maximum values are shown as window field max of 65,535, scale factor max of 14 giving multiplier 16,384, and resulting maximum window of approximately 1 GB. The scale factor is fixed for the duration of the connection once negotiated. It cannot be changed without closing and reopening the connection. Both directions of the connection can use different scale factors, as each side advertises its own value independently. Selective Acknowledgement -SACK. Selective acknowledgement, known as SACK, dramatically improves TCP's ability to recover from multiple packet losses. Without SACK, TCP's cumulative acknowledgement system requires retransmission of all data following a loss, even if some of that data already arrived successfully. SACK allows the receiver to inform the sender exactly which segments have been received, enabling targeted retransmission of only the missing data. SACK uses two related options. The SACK permitted option, with kind value 4, is sent in SYN segments to indicate support for SACK. It contains no data, just the kind and length bytes. Both endpoints must include SACK permitted in their SYN segments for SACK to be enabled on the connection. The SACK option itself, with kind value 5, carries the actual acknowledgement data. It contains one or more SACK blocks, where each block specifies a contiguous range of read bytes using left edge and right edge sequence numbers. The left edge is the first sequence number of read data, and the right edge is the sequence number immediately following the last read byte in that block. The diagram illustrates how SACK blocks describe received data. The data stream shows segments as they should arrive in order. Segments 1000 through 1999 and 2000 through 2999 arrive successfully, but segment 3000 through 3999 is lost. Then segments 4000 through 4999 and 5000 through 5999 arrive successfully, but segment 6000 through 6999 is also lost. Finally, segments 7000 through 7999 and 8000 through 8999 arrive successfully. The cumulative ACK can only acknowledge through 2999, the last in order byte. However, SACK blocks provide additional information. The first SACK block spans 4000 to 6000, indicating bytes 4000 through 5999 are received. The second SACK block spans 7000 to 9000, indicating bytes 7000 through 8999 are received. With this information, the sender knows to retransmit only segments 3000 and 6000, not everything from 3000 onward. SACK is particularly valuable on lossy networks or when multiple packets are lost in a single congestion event. It reduces unnecessary retransmissions and accelerates recovery, significantly improving throughput in challenging conditions. TCP timestamps option. The TCP timestamps option serves two important purposes: accurate round-trip time measurement and protection against wrapped sequence numbers. Both capabilities become increasingly important on high-speed networks. The timestamps option, with kind value 8, contains two 32-bit values. The first is TS-val, the timestamp value, which is the sender's current timestamp. The second is TSECR, the timestamp echo reply, which echoes back the timestamp from the most recently received segment. When a sender receives an acknowledgement, it can subtract the echoed timestamp from its current time to calculate the round-trip time for that data. For RTT measurement, timestamps provide more accurate data than the traditional method of measuring one segment per RTT. The traditional method samples RTT only when the time segment is acknowledged, which may not represent current conditions. With timestamps, every acknowledgement provides an RTT sample, enabling faster adaptation to changing network conditions. Protection against wrapped sequence numbers, called PAWS, addresses a problem on very high-speed links. The 32-bit sequence number space of about 4.3 billion bytes can wrap around in seconds on 10 gigabits per second or faster links. If an old, delayed packet arrives after the sequence numbers have wrapped, it might be accepted as valid new data. PAWS uses timestamps to reject such segments. If a segment's timestamp is older than the last received timestamp, it must be a delayed duplicate and is discarded. The diagram shows the timestamp's option structure and operation. The TS-val field contains the sender's current timestamp clock value when the segment is sent. The TSECR field contains the timestamp value copied from the most recently received segment from the peer. When the sender transmits data, it sets TS-val to its current time T1 and TSECR to the last received timestamp from receiver. When the receiver acknowledges, it sets TS-val to its current time and TSECR to T1, echoing the sender's timestamp. When the sender receives this ACK at time T2, RTT equals T2 minus T1, calculated from the echoed timestamp. For PAWS, if a segment arrives with a timestamp older than the previous segment's timestamp, the segment is discarded as a delayed duplicate. TCP Options Summary. TCP options extend the protocol's capabilities to meet the demands of modern networks. Through careful negotiation during connection establishment, endpoints can agree on enhanced features that improve performance, reliability, and scalability. Maximum segment size prevents IP fragmentation by ensuring segments fit within the path MTU. It is negotiated once during the handshake and remains fixed for the connection. Proper MSS selection maximizes throughput while avoiding the overhead and reliability issues of fragmentation. Window scale overcomes the 16-bit window limitation, enabling windows up to 1 GB. This is essential for achieving high throughput on long-fat networks, those with high bandwidth and high latency. Both endpoints must support scaling for it to be enabled. Selective acknowledgment transforms loss recovery from a sequential process to a parallel one. By informing the sender exactly which segments arrived, SACK enables targeted retransmission of only missing data. This dramatically improves performance when multiple segments are lost. Timestamps provide accurate RTT measurement for every segment and protect against wrapped sequence numbers on high-speed links. The continuous RTT feedback helps TCP adapt quickly to changing network conditions, while PAWS prevents data corruption from delayed duplicates. The summary diagram shows all four options and their relationships. TCP options connects to four branches. MSS handles segment sizing with function to prevent fragmentation and path MTU coordination. Window scale handles large windows with function to overcome 16-bit limit for high-speed links. SACK handles loss recovery with function for precise identification of missing segments and efficient retransmission. Timestamps handles RTT and pause with function for accurate timing and protection against sequence wrap. All four options converge on enhanced TCP performance, representing the collective benefit of modern TCP optimizations. Together, these options transform TCP from its original 1980s design into a protocol capable of efficiently utilizing today's high-speed networks. In the next section, we will explore TCP congestion control, examining how TCP detects and responds to network congestion to achieve fair and efficient use of shared network resources. Introduction to Congestion Control. Welcome back to our TCP series. In this section, we explore TCP congestion control, one of the most sophisticated and important aspects of the protocol. While flow control prevents overwhelming the receiver, congestion control prevents overwhelming the network itself. Without congestion control, the internet would collapse under the weight of unregulated traffic. Network congestion occurs when more data enters a network segment than it can handle. Routers have finite buffer space and processing capacity. When buffers fill up, packets are dropped. When processing capacity is exceeded, delays increase. These symptoms, packet loss and increased latency, are the primary signals TCP uses to detect congestion. The fundamental challenge of congestion control is that no single sender knows the network's total capacity or how many other senders are competing for that capacity. Each TCP connection must independently probe for available bandwidth, back off when congestion is detected, and share network resources fairly with other connections. This distributed algorithm, running on millions of devices simultaneously, keeps the internet functioning. The diagram illustrates how congestion develops in a network. Multiple senders, labeled sender 1 through sender n, all transmit data toward the network. Their traffic converges at a router, which has limited buffer capacity. The router forwards traffic to the receiver. When the combined input rate exceeds the router's output capacity, the buffer begins to fill. Once the buffer reaches capacity, arriving packets are dropped. These dropped packets must be retransmitted, creating even more traffic and potentially worsening congestion. The congestion collapse scenario shows how uncontrolled sending can lead to network saturation where effective throughput drops to near zero despite maximum transmission attempts. TCP's congestion control algorithms have evolved significantly since the protocol's creation. The original TCP had no congestion control, leading to congestion collapse events in the late 1980s. Van Jacobson's seminal work introduced the algorithms we still use today, including slow start and congestion avoidance. Slow start algorithm. Slow start is TCP's mechanism for probing network capacity at the beginning of a connection or after a timeout. Despite its name, slow start actually increases the congestion window quite rapidly, doubling it with each round trip time. The name comes from the fact that it starts from a small initial value rather than immediately sending at full speed. When a TCP connection begins, the sender has no information about network capacity. The initial congestion window is typically set to a small value, historically 1 segment but now commonly 10 segments as specified in RFC 6928. This conservative start ensures the sender does not immediately flood an unknown network. During slow start, the congestion window increases by 1 maximum segment size for each acknowledgment received. Since a window's worth of data generates a window's worth of acknowledgments, the effective result is that CWND doubles every round trip time. If CWND starts at 1 maximum segment size, after 1 RTT it becomes 2 maximum segment sizes, then 4, then 8, then 16, and so on. This exponential growth quickly probes for available bandwidth. Slow start continues until one of 3 things happens. First, the congestion window reaches the slow start threshold, SSTHRESH, at which point TCP transitions to the more conservative congestion avoidance phase. Second, packet loss is detected, indicating congestion and triggering a reduction in CWND. Third, the congestion window reaches the receive window, meaning the receiver's capacity is now the limiting factor. The diagram visualizes slow start growth over time. The vertical axis represents congestion window size in segments, and the horizontal axis represents time in round-trip times. Starting at RTT0, CWND equals 1 segment. At RTT1, after receiving the first ACK, CWND grows to 2 segments. At RTT2, 2 ACKs arrive and CWND grows to 4 segments. At RTT3, 4 ACKs grow CWND to 8 segments. At RTT4, 8 ACKs grow CWND to 16 segments. The growth pattern shows exponential increase, with the window doubling each RTT. A horizontal dashed line indicates SS thresh, the slow start threshold. When CWND reaches SS thresh, the algorithm transitions from slow start to congestion avoidance, where growth becomes linear rather than exponential. Detecting congestion space packet loss. TCP interprets packet loss as a signal of network congestion. While packets can be lost for other reasons, such as bit errors or routing failures, congestion is by far the most common cause. Therefore, TCP reacts to all loss events by reducing its sending rate, on the assumption that congestion is responsible. TCP detects packet loss through 2 mechanisms: retransmission timeout and duplicate acknowledgments. These mechanisms indicate different severity of congestion and trigger different responses. A retransmission timeout, or RTO, occurs when an acknowledgment fails to arrive within the expected time. This typically indicates severe congestion where multiple packets have been lost, or where the network path has failed entirely. The timeout threshold is calculated based on smooth or TT measurements. As we discussed earlier, when a timeout occurs, TCP assumes significant congestion and responds aggressively by reducing congestion window to one segment and restarting slow start. 3 duplicate acknowledgments indicate that some packets are getting through but at least one was lost. As we discussed in the SACK section, out-of-order arrivals trigger duplicate ACKs. 3 duplicates strongly suggest loss rather than mere reordering. This scenario indicates moderate congestion where the network is still functioning but at reduced capacity. TCP responds with fast retransmit and fast recovery, which are more moderate than the timeout response. The diagram shows both loss detection mechanisms. In the timeout path, the sender transmits data and starts a timer. No ACK arrives, and when the timer expires, this signals severe congestion. The response is to set congestion window to 1 MSS and SS thresh to half the previous congestion window, then restart with slow start. In the duplicate ACKs path, the sender transmits multiple segments. Some arrive successfully, but one is lost. The receiver sends duplicate ACKs for the missing segment. After 3 duplicates arrive, this signals moderate congestion. The response is fast retransmit of the missing segment followed by fast recovery, which halves congestion window but avoids returning to slow start. The timeout path shows the more drastic response, while the duplicate ACK path shows the lighter weight response to less severe congestion. Fast recovery. Fast recovery is the companion algorithm to fast retransmit. While fast retransmit handles the immediate retransmission of the lost segment, fast recovery manages the congestion window during the recovery period. Together, these algorithms allow TCP to recover from isolated losses without reverting to slow start. When fast retransmit is triggered, TCP enters fast recovery mode. The first action is to record the current congestion window and set SST-resh to half of CWND. This captures the sender's estimate of a safe operating point based on where congestion occurred. Next, CWND is set to SS-thresh plus 3 segments. The plus 3 accounts for the 3 duplicate ACKs that triggered fast retransmit, representing 3 segments that have left the network and reached the receiver. By crediting these segments, TCP maintains a more accurate picture of how much data is actually in flight. While in fast recovery, each additional duplicate ACK increases congestion window by 1 segment. This inflation reflects that each duplicate ACK indicates another segment has reached the receiver and left the network. The sender can transmit new data as congestion window grows, maintaining data flow during recovery. Fast recovery ends when an ACK arrives for new data, specifically an ACK that acknowledges the retransmitted segment and beyond. At this point, congestion window is set to slow start threshold, the value saved when entering fast recovery. The connection then continues in congestion avoidance mode with this reduced window. The diagram shows the fast recovery state machine. From the normal operation state, receiving 3 duplicate ACKs triggers a transition to fast recovery. Upon entry, SS-thresh is set to CWND divided by 2, and CWND is set to SS-thresh plus 3 MSS. While in fast recovery, each duplicate ACK increases CWND by 1 MSS. When a new ACK arrives acknowledging the retransmitted data, CWND is set to SS-thresh and the connection transitions to congestion avoidance mode. From congestion avoidance, another loss event of 3 duplicate ACKs would again enter fast recovery. If a timeout occurs in any state, SS-thresh is set to CWND divided by 2, CWND is set to 1 MSS, and the connection transitions to slow start, the most conservative response. TCP congestion control state machine. The various congestion control phases and their transitions can be visualized as a state machine. Understanding this state machine helps predict TCP behavior under different network conditions and assists in troubleshooting performance problems. A new connection starts in the slow start state with CWND set to the initial window, typically 10 segments, and SSTHRESH set to a large value, effectively infinity. In this state, CWND doubles every RTT as acknowledgments arrive. From slow start, there are three possible transitions. If SYN window reaches slow start threshold, the connection moves to congestion avoidance where growth becomes linear. If three duplicate ACKs arrive indicating loss, the connection enters fast recovery after setting slow start threshold to half of SYN window. If a timeout occurs, slow start threshold is set to half of SYN window. SYN window is reset to one segment, and the connection remains in slow start but with the reduced slow start threshold value. In congestion avoidance, CWND grows by one segment per RTT. The transitions are similar to slow start. Three duplicate ACKs trigger fast recovery, and timeout resets to slow start with CWND of one segment. There is no transition back to slow start from congestion reaching SSTHRESH because once in congestion avoidance, the connection has already passed SSTHRESH. Fast recovery is entered after three duplicate ACKs trigger fast retransmit. The connection inflates congestion window as duplicate ACKs continue arriving, allowing new data transmission during recovery. When a new ACK arrives covering the retransmitted data, the connection transitions to congestion avoidance with congestion window set to slow start threshold. A timeout during fast recovery moves to slow start. The complete state machine diagram shows all states and transitions. The slow start state shows congestion window doubling per RTT with initial congestion window equal to IW and slow start threshold equal to infinity. An arrow labeled congestion window reaches slow start threshold leads to congestion avoidance, where congestion window increases by 1 MSS per RTT. From both states, an arrow labeled 3 DUP ACKs leads to fast recovery, where slow start threshold becomes congestion window divided by 2 and congestion window becomes slow start threshold plus 3 MSS. In fast recovery, duplicate ACKs increase congestion window by 1 MSS. A new ACK arrow from fast recovery leads back to congestion avoidance with congestion window set to slow start threshold. From all three states, a timeout arrow leads back to slow start with congestion window reset to 1 MSS and slow start threshold set to congestion window divided by 2. This comprehensive diagram captures all possible state transitions in TCP Reno-style congestion control. Congestion control summary. TCP congestion control is a distributed algorithm that enables millions of connections to share network resources fairly and efficiently. Through careful management of the congestion window, TCP probes for available bandwidth, detects congestion through packet loss, and responds by reducing its sending rate. Slow start provides rapid initial probing, doubling the congestion window each RTT until reaching the slow start threshold or detecting loss. This allows new connections to quickly find available capacity without prior knowledge of network conditions. Congestion avoidance provides gentle steady-state probing, increasing the congestion window by 1 segment per RTT. This linear growth seeks additional capacity without risking severe congestion, operating in a region where the network is near capacity. Fast retransmit and fast recovery enable efficient loss recovery. Rather than waiting for timeouts, TCP uses duplicate acknowledgments to detect loss quickly and retransmit immediately. Fast recovery maintains data flow during recovery by managing the congestion window intelligently. The AIMD pattern, combining additive increase during probing with multiplicative decrease on loss, provides proven fairness and stability properties. Connections converge toward equal shares of bottleneck bandwidth regardless of starting conditions. The summary diagram recaps all congestion control components. TCP congestion control sits as the central concept, connecting to 4 major mechanisms: Slow start handles initial probing with exponential growth where CWND doubles per RTT until reaching SS thresh. Congestion avoidance handles steady-state probing with linear growth where CWND increases by 1 MSS per RTT. Fast retransmit and fast recovery handle loss recovery, quickly retransmitting on 3 duplicate ACKs and maintaining flow during recovery. The AIMD pattern captures the fairness mechanism with additive increase plus multiplicative decrease equaling convergence to fair shares. All 4 components work together to achieve the ultimate goal of efficient fair network sharing, where multiple connections coexist without overwhelming the network while each receiving a reasonable share of available bandwidth. In the next section, we will explore TCP connection termination, examining how connections close gracefully through the 4-way handshake, the various TCP states during termination, and the important time wait state. Introduction to connection termination. Welcome back to our TCP series. In this section, we explore how TCP connections are terminated. Just as establishing a connection requires a careful handshake to synchronize both parties, terminating a connection requires a structured process to ensure all data has been delivered and both sides agree the connection is finished. TCP provides 2 methods for ending a connection: graceful termination using the FIN flag and abrupt termination using the RST flag. Graceful termination is the normal method, allowing both sides to finish sending data and confirm receipt before closing. Abrupt termination immediately discards the connection, typically used in error conditions or when an application crashes. The graceful termination process is often called the 4-way handshake, though it can sometimes be reduced to 3 messages when FIN and ACK are combined. Unlike the 3-way handshake for connection establishment, termination requires 4 messages because each direction of the full duplex connection must be closed independently. Understanding connection termination is important for several reasons. It helps diagnose connection issues where one side believes the connection is open while the other considers it closed. It explains the time wait state that can accumulate on busy servers. And it clarifies why connections sometimes hang in unusual states when things go wrong. The diagram shows the 2 termination methods. The graceful close path shows an active close initiator that sends a FIN segment to the passive close responder. The passive close responder acknowledges with ACK, then sends its own FIN when ready. The active close initiator acknowledges this final FIN, completing the 4-way exchange. Both sides transition through defined states before reaching close. The abrupt close path shows a sender transmitting an RST segment. Upon receiving RST, the recipient immediately discards all connection state and transitions directly to closed without any acknowledgement or further exchange. The graceful method ensures data integrity while the abrupt method prioritizes speed over reliability. 4-way handshake step by step. Let us examine each step of the 4-way handshake in detail to understand the message contents and state transitions. In step 1, the active closer sends a FIN segment. This segment has the FIN flag set to indicate no more data will be sent in this direction. The ACK flag is also set because, in an established connection, all segments carry acknowledgments. The sequence number represents the last byte of data plus 1. As the FIN consumes 1 sequence number just like send is. After sending, the active closer enters FIN wait 1 state. In step 2, the passive closer acknowledges the FIN. Upon receiving the FIN, the passive closer sends an ACK segment. The acknowledgement number is the active closer's sequence number plus 1, confirming receipt of the FIN. The passive closer enters close wait state and notifies its application that the peer has finished sending. The application can continue sending data if needed. In step 3, the passive closer sends its own FIN. When the passive closer's application has finished sending data and calls close on the socket, TCP sends a FIN segment. This FIN may be delayed if the application has more data to send after receiving notification of the peer's FIN. After sending its fin, the passive closer enters last_ACK state. In step 4, the active closer acknowledges the final FIN. Upon receiving the passive closer's FIN, the active closer sends an ACK and enters time_wait state. This final ACK confirms receipt of the FIN. The passive closer, upon receiving this ACK, immediately transitions to closed state. The active closer remains in time_wait for a specified duration before also transitioning to closed. The diagram breaks down each step with segment details. The half-close state. The half-close is a unique feature of TCP that allows one direction of a connection to be closed while the other remains open. This occurs between the first FIN being acknowledged and the second FIN being sent. Understanding half-close is important for protocols that use this capability and for troubleshooting connections that appear stuck. When the active closer sends a FIN, it signals that it has no more data to send. However, this does not mean the connection is fully closed. The active closer can still receive data from the passive closer. The passive closer's send path remains fully operational until it sends its own FIN. During half-close, the passive closer is in close wait state. Its application has been notified that the peer finished sending through a read operation returning 0 bytes or an end-of-file indicator. The application can continue processing and send response data back to the active closer. Some protocols deliberately use half-close. For example, an HTTP client might send a complete request and then half-close its sending direction. The server continues sending the response over the still open return path. This signals completion without requiring application layer framing. The diagram illustrates the half-close data flow. The active closer sends a FIN to the passive closer, indicating the active closer direction is closed. The active closer is now in FIN_wait_2 state while the passive closer is in close_wait state. Despite the FIN in one direction, the passive closer to active closer direction remains open. The passive closer can send multiple data segments to the active closer, which are acknowledged normally. The active closer receives this data and sends ACKs back. This continues until the passive closer has no more data to send. Finally, the passive closer sends its FIN, and the active closer responds with ACK, completing the termination. The diagram shows data flowing in one direction while the other direction is already closed, demonstrating the half-duplex phase. Termination states in detail. The termination-related states require careful attention because connections can sometimes get stuck in these states, causing resource exhaustion or preventing new connections. FIN_WAIT_1 is entered when an application calls close and TCP sends a FIN. The connection is waiting for acknowledgement of its FIN. From here, receiving ACK moves to FIN_WAIT_2, or receiving FIN simultaneously moves to closing in the case of simultaneous close. FIN_WAIT_2 indicates our FIN has been acknowledged, but we are waiting for the peer's FIN. The connection is half-closed at this point. Data can still arrive from the peer. A connection can remain in FIN_WAIT_2 indefinitely if the peer never closes, which is why some systems implement a FIN_WAIT_2 timeout. Close wait indicates we received a FIN from the peer and have acknowledged it, but our application has not yet closed the socket. A connection stuck in close wait usually indicates an application bug where the application failed to close the socket after the peer disconnected. This is a common source of resource leaks. Closing is a rare state that occurs during simultaneous close, where both sides send FIN at approximately the same time before receiving the other's FIN. Each side receives FIN while in FIN_WAIT_1 and transitions to closing. Last acknowledge is entered after sending a FIN in response to receiving a FIN. The connection is waiting for acknowledgement of its FIN before transitioning to closed. Time wait is entered by the side that sends the final ACK of the four-way handshake. This critical state is explained in detail on the next slide. The time wait state. Time wait is one of the most important and often misunderstood TCP states. The active closer enters time wait after sending the final ACK of the four-way handshake. The connection remains in this state for a duration called 2 times MSL, which is twice the maximum segment lifetime, before transitioning to closed. The maximum segment lifetime is the maximum time a TCP segment can exist in the network before being discarded. Our FC 793 defines MSL as 2 minutes, though many implementations use 30 seconds or 1 minute. The 2MSL timer therefore ranges from 1 to 4 minutes depending on the implementation. Time wait serves two critical purposes. First, it ensures the final ACK has time to reach the passive closer. If the final ACK is lost, the passive closer will retransmit its FIN. The active closer must remain able to respond to this retransmission, which it can only do if it remains in time wait. Without time wait, the active closer might have fully closed and would respond to the retransmitted FIN with or ST, confusing the passive closer. Second, time wait prevents old duplicate segments from being confused with new connections. After a connection closes, a new connection could be established using the same 4-tuple of source IP, source port, destination IP, and destination port. If segments from the old connection are still wandering in the network, they could be misinterpreted as belonging to the new connection. Time wait ensures all old segments have expired before the 4-tuple can be reused. The diagram explains time wait purposes visually. The first scenario shows lost ACK recovery. The active closer sends the final ACK, which is lost in the network. The passive closer, not receiving ACK, retransmits its FIN. Because the active closer is in time wait, it can receive this retransmitted FIN and send ACK again. The second scenario shows old duplicate prevention. After a connection closes, old delayed segments might still exist in the network. If a new connection with the same 4-tuple starts immediately, these old segments could corrupt the new connection's data. Time wait of 2 times MSL ensures all old segments have been discarded before the 4-tuple can be reused. Both purposes combine to ensure reliable connection termination and clean connection reuse. Abrupt connection termination or ST. The ST flag provides an alternative to graceful termination, allowing immediate connection abort. When a segment with ST set is received, the connection is immediately discarded without any acknowledgement or further exchange. ST is used in specific scenarios where graceful termination is impossible or undesirable. ST is sent automatically in several situations. When a segment arrives for a connection that does not exist, such as after a server crash and restart, the receiver sends ST to inform the sender the connection is gone. When a segment arrives that is unacceptable for the current connection state, ST may be sent. When an application wants to abort a connection immediately without graceful close, it can trigger ST. Unlike FIN, RST is not acknowledged. The receiver simply discards all connection state and returns to closed. Any data in transit or in buffers is lost. This makes RST fast but potentially destructive, as data that was sent but not acknowledged will never be retransmitted. Applications can explicitly trigger ST through the SO linger socket option. Setting SO linger with a 0 timeout causes close to send ST instead of FIN. This is sometimes used when an error is detected and the application wants to signal abnormal termination to the peer, or when the application does not care about buffered data. ST is also involved in various attack scenarios. ST injection attacks send forged ST segments to terminate legitimate connections. This is mitigated by ST validation rules that require the sequence number to be within the receive window, and some systems require exact sequence number match. The sequence diagram compares graceful and abrupt termination. The graceful termination path shows host A sending FIN, host B sending ACK, host B sending FIN, and host A sending final ACK, with both sides transitioning through states before reaching closed. This ensures all data is delivered. The abrupt termination path shows host A sending RST. Host B receives RST and immediately transitions to closed with no response sent. Host A also immediately transitions to close. Any unacknowledged data is lost, but termination is instantaneous. The diagram emphasizes that RST provides speed at the cost of data reliability. Connection termination summary. TCP connection termination ensures reliable closure of full duplex connections. The four-way handshake allows each direction to close independently, with proper acknowledgement of all transmitted data before final closure. The four-way handshake involves FIN and ACK exchanges from both sides. The active closer sends the first FIN, the passive closer acknowledges and later sends its own FIN, and the active closer sends the final ACK. This process can be shortened when FIN and ACK are combined in a single segment. TCP states track the connection through its lifecycle. Established represents normal operation. The termination states FIN _wait _1, FIN _wait _2, close _wait, closing, last _ACK, and time _wait guide the connection through orderly shutdown. Each state represents a specific phase with defined transitions. Time wait is essential for reliable termination. It ensures the final ACK reaches the passive closer and allows time for old segments to expire. The 2MSL duration prevents problems from lost acknowledgements and duplicate segments. Managing time wait accumulation is important for busy servers. RST provides abrupt termination when needed. Unlike graceful termination, RST immediately destroys the connection without acknowledgement. It is used for error conditions, non-existent connections, and application-requested aborts. RST sacrifices data reliability for speed. The summary diagram shows all connection termination concepts. TCP connection termination branches into two methods. Graceful termination uses the four-way handshake with FIN and ACK exchanges, supports half-close for unidirectional closure, and enters time wait for reliability. Abrupt termination uses RST for immediate close with no acknowledgement required. The TCP state section shows the progression from established through FIN _wait _1, FIN _wait _2, close wait, closing, last ACK, and time wait, ultimately reaching close. All components work together to provide both reliable graceful termination and fast emergency termination as appropriate for each situation. In the next section, we will explore additional TCP mechanisms including Nagel's algorithm, delayed acknowledgements, and TCP keep alive, which optimize TCP behavior for different application patterns. Introduction to Nagel's algorithm. Welcome back to our TCP series. In this section, we explore several important TCP mechanisms that optimize network efficiency and handle special situations. We begin with Nagel's algorithm, a clever optimization that reduces network congestion caused by small packets. In the early days of networking, a problem emerged with interactive applications like Telnet. Users would type one character at a time, and each keystroke would generate a separate TCP segment. A single character requires at least 40 bytes of headers, 20 for IP and 20 for TCP, creating a 41-byte packet to transmit 1 byte of actual data. This extreme inefficiency was called the small packet problem. John Nagel observed this problem in 1984 and proposed a simple but elegant solution now known as Nagel's algorithm, documented in our FC 896. The algorithm reduces the number of small packets on the network by buffering small writes until certain conditions are met, then sending the accumulated data as a single larger packet. The core principle of Nagel's algorithm is straightforward. If there is unacknowledged data in flight, buffer any new small data until either an acknowledgement arrives or enough data accumulates to fill a maximum segment. This allows multiple small writes to be combined into fewer, larger packets. The diagram illustrates the small packet problem and Nagel's rule. The without Nagel section shows an application making individual writes of 1 byte, 1 byte, and 1 byte. Each write immediately becomes a separate packet, resulting in 3 packets of 41 bytes each carrying just 1 byte of data, totaling 123 bytes of network traffic for 3 bytes of data. The with Nagel section shows the same application writes of 1 byte each. The first write is sent immediately as a 41-byte packet. The subsequent writes are buffered while waiting for the ACK. When the ACK arrives, the buffered 2 bytes are sent together in a single 42-byte packet. The total network traffic is reduced to 83 bytes, a significant improvement in efficiency. Nagel's algorithm trade-offs. While Nagel's algorithm improves network efficiency, it introduces latency for small writes. This trade-off between efficiency and latency makes Nagel's algorithm problematic for certain applications, leading to the TCP_no delay socket option that disables it. The latency impact is most noticeable in request-response protocols where small messages are exchanged. Consider a client sending a small request while previous data remains unacknowledged. Nagel's algorithm buffers the request, waiting for an ACK. The server cannot respond until it receives the request, and the client is waiting for data from the server. This can add significant delay to each transaction. Interactive applications like games, remote desktop protocols, and real-time communication suffer from Nagel-induced latency. Users perceive lag between their actions and the response. In these applications, minimizing latency is more important than maximizing network efficiency. The TCP_no delay socket option disables Nagel's algorithm for a connection. When set, all data is sent immediately regardless of size or outstanding acknowledgments. This restores immediate transmission at the cost of potentially sending many small packets. The sequence diagram contrasts behavior with and without TCP_no delay. In the with Nagel scenario, the client sends a small request while other data is unacknowledged. The request is buffered waiting for ACK. Eventually, the ACK arrives and the buffered request is finally sent. The server receives the delayed request and sends a response. The total time includes buffering delay. In the without Nagel scenario using TCP_no delay, the client sends the small request immediately without buffering. The request goes directly to the server with no delay. The server responds promptly. The total time is reduced by eliminating the buffering delay. The diagram shows how TCP_no delay reduces latency at the cost of sending smaller packets. Nagel and delayed ACK interaction. A notorious problem arises when Nagel's algorithm on the sender interacts with delayed acknowledgments on the receiver. This interaction can cause significant latency, sometimes called the Nagel delayed ACK problem or the 200 milliseconds delay problem. Consider a sender making 2 small writes. The first write is sent immediately because no data is outstanding. The receiver gets this data and starts its delayed acknowledgement timer, waiting to see if more data arrives or if it has data to send. Meanwhile, the sender makes its second write. Because data is now outstanding and the new write is small, Nagel's algorithm buffers it, waiting for an acknowledgement. Now both sides are waiting. The sender waits for an ACK to release the buffered data. The receiver waits for its delayed ACK timer to expire or for more data to trigger an immediate ACK. Neither condition is met until the timer expires, typically 200 milliseconds later. This delay occurs even on fast networks where the RTT might be just a few milliseconds. The solution to this problem depends on the application pattern. If the application naturally writes request-response patterns where a complete message is written then a response is expected, Nagel's algorithm should be disabled with TCP_no delay. If the application writes large amounts of data in many small pieces, Nagel is beneficial and the application should use larger writes or explicitly flush at message boundaries. The sequence diagram illustrates the problematic interaction. The sender writes and sends small write 1. The receiver gets the data and starts a 200 milliseconds delayed ACK timer. The sender then makes small write 2, which Nagel buffers because write 1 is unacknowledged. The sender enters a waiting state. Time passes, shown by a dashed line labeled 200 milliseconds delay. Eventually, the receiver's delayed ACK timer expires, and the receiver sends an ACK. Only now does the sender receive the ACK and send the buffered write 2. The diagram clearly shows how the combination of both algorithms creates unnecessary delay that neither algorithm alone would cause. TCP Keep Alive Introduction. TCP Keep Alive is a mechanism for detecting dead connections and keeping connections alive through firewalls and NAT devices. Without Keep Alive, a TCP connection can remain open indefinitely even if the remote host has crashed or become unreachable, wasting resources and causing application hangs. The problem Keep Alive solves involves idle connections. Once a TCP connection is established, it can remain idle indefinitely with no packets exchange. TCP has no inherent timeout for idle connections. If one endpoint crashes without sending FIN or RST, the other endpoint has no way to know the connection is dead until it tries to send data and the transmission fails. Consider a scenario where a client opens a connection to a server, then the client machine crashes or loses network connectivity. The server has no way to know this happened. The connection appears open from the server's perspective, consuming memory and possibly file descriptors. If the server waits for the client to send a request, it could wait forever. TCP Keep Alive addresses this by periodically sending probe packets on idle connections. If the probes receive responses, the connection is still alive. If probes go unanswered, the connection is considered dead and is closed. This provides a way to detect dead peers and clean up stale connections. The diagram illustrates the dead connection problem and Keep Alive solution. In the problem scenario, the client establishes a connection with the server. The client then crashes with no FIN or RST sent. The server, unaware of the crash, enters a waiting indefinitely state, showing a resource leak. No packets are exchanged, and the server never learns the connection is dead. In the Keep Alive solution scenario, the client establishes a connection with the server. The client then crashes. After an idle timeout period, the server sends a Keep Alive probe. The probe receives no response because the client is gone. After multiple failed probes, the server detects dead connection and closes it, freeing the connection closed resources. The diagram shows how Keep Alive transforms an indefinite resource leak into a bounded detection and cleanup process. Configuring TCP Keep Alive. TCP Keep Alive can be configured at both the system level and per socket. System-level settings provide defaults for all connections, while per-socket configuration allows applications to customize behavior for specific connections. On Linux, system-wide defaults are controlled through SYS control parameters. The TCP_Keep Alive_time parameter sets the idle time before probing begins. The TCP_Keep Alive_interval parameter sets the interval between probes. The TCP_Keep Alive_probes parameter sets the number of failed probes before closing. Changes to these parameters affect new connections but not existing ones. Per socket configuration uses socket options. The SO_KEEPALIVE option enables Keep Alive for a specific socket. Without this option set, the connection does not use Keep Alive regardless of system settings. The TCP_KEEPIDLE, TCP_KEEPINTVL, and TCP_KEEPCNT options override the system defaults for individual sockets. Applications should enable Keep Alive on connections that may be idle for extended periods, particularly server-side connections where clients might disappear. The configuration should balance detection speed against probe traffic. Very aggressive settings can generate significant traffic when many idle connections exist. Cloud environments and containerized applications often require more aggressive keep-alive settings. Load balancers, firewalls, and NAT devices typically have their own idle timeouts, often around 5 to 15 minutes. If TCP keep alive does not send probes within this window, the intermediary may drop the connection, causing silent failures when traffic resumes. The code block shows complete configuration examples. The Linux system-wide section shows sysctl commands to set TCP_keep-alive_time to 60 seconds, TCP_keep-alive_intbl to 10 seconds, and TCP_keep-alive_probes to 6 probes. The per socket in C section shows the set sock opt calls to enable SO_KEEPALIVE, then set TCP_KEEPIDLE to 60, TCP_KEEPINTBL to 10, and TCP_KEEPCNT to 6. The Python example section shows similar configuration using sock.setSockOpt with socket.sol_socket for SO_KEEPALIVE and socket.IPPROTO_TCP for the TCP specific options. All examples configure the same aggressive 60-second idle time with 10-second probe intervals and 6 probe attempts. TCP optimization summary. The mechanisms we have covered in this section, Nagel's algorithm, delayed acknowledgments, and TCP keep alive, represent important optimizations and operational considerations for TCP connections. Understanding when and how to use them is essential for building performant networked applications. Nagel's algorithm reduces small packet overhead by buffering small writes until acknowledgement arrives or a full segment accumulates. It is beneficial for bulk transfers but harmful for latency-sensitive applications. The TCP_NODELAY socket option disables it when low latency is more important than efficiency. Delayed acknowledgments reduce ACK packet overhead by waiting briefly before sending acknowledgments, allowing piggybacking on data or batching multiple ACKs. The interaction between Nagel's algorithm and delayed ACKs can cause the 200 millisecond delay problem, which is resolved by disabling Nagel on the sender. TCP keep alive detects dead connections and maintains connections through intermediaries with idle timeouts. The default configuration is very conservative, taking over 2 hours to detect a dead peer. Most applications benefit from more aggressive configuration, especially in cloud and containerized environments with NAT and load balancers. These mechanisms interact with each other and with application behavior. The best configuration depends on the specific application, its communication patterns, and the network environment. Testing under realistic conditions is essential to validate that the chosen configuration provides the desired behavior. The summary diagram shows all 3 mechanisms and their relationships. TCP optimizations branches into 3 main mechanisms. Nagel's algorithm handles small packet reduction, buffering small writes until ACK or full segment, and can be disabled with TCP_NODELAY. Delayed ACK handles ACK packet reduction, waiting to piggyback or batch acknowledgements, with typical delay around 200 milliseconds. TCP keep alive handles dead connection detection, probing idle connections to detect crashed peers, and is configurable for speed versus traffic trade-off. An interaction note shows that Nagel plus delayed ACK can cause the 200 milliseconds delay problem, which is resolved by TCP_NODELAY. All 3 mechanisms contribute to building efficient, reliable applications that balance network efficiency with application responsiveness. Thank you for your attendance. Please consider subscribing to the channel and liking this video.